Welcome. Today we're diving into HTTP sessions and private network connectivity in Cloud Run. This is an essential topic for building robust web applications in Google Cloud's serverless environment. HTTP sessions allow web applications to remember information about users across multiple requests. Think of it like a conversation. Each HTTP request is independent, but sessions help maintain context between them. Sessions store various types of user state data. For example, whether a user is logged in, what items are in their shopping cart, their preferences, and their navigation history. This data needs to persist across multiple page requests. In Cloud Run's serverless environment, your application runs across multiple independent instances. Each instance can handle requests, but they don't share memory. This creates a challenge for session management. When a user makes multiple requests, they might hit different instances each time. Since instances don't share memory, session data stored locally would be lost between requests. This is where external session storage becomes essential. The solution involves using external session storage like Memory Store for Redis. Cloud Run connects to Memory Store through a VPC connector, which acts as a secure bridge to private Google Cloud resources. This architecture provides persistent session storage that's shared across all Cloud Run instances, offers high performance with Redis, and maintains secure private connectivity through the VPC network. Throughout this series, we'll explore the challenges of session storage in serverless environments, learn about Redis and Memory Store benefits, understand VPC connector setup, cover security best practices, and walk through hands-on implementation. Let's begin this journey into Cloud Run session management. Cloud Run containers are fundamentally different from traditional servers. They are designed to be stateless and completely disposable, which creates unique challenges for session management. Here we see a Cloud Run container with session data stored directly inside it. This might seem logical at first. Keep the user's session information right where the application is running. As traffic increases, Cloud Run automatically creates more container instances to handle the load. Each container runs independently and can store its own session data. But here's the critical problem. Cloud Run containers are disposable. When traffic decreases or for maintenance or simply due to Google's infrastructure management, containers can be terminated at any time. Imagine you're shopping online and you've carefully selected items for your cart. You've spent time comparing products, reading reviews, and building up a substantial order. Now imagine that every time you click a link, refresh the page, or even just wait too long, your entire shopping cart disappears. All your carefully selected items are gone, and you have to start over from scratch. This happens because Cloud Run containers are ephemeral. Google's infrastructure can terminate them for various reasons: scaling down during low traffic, performing maintenance, optimizing resources, or updating the underlying infrastructure. When a container terminates, everything stored in its local memory or file system is permanently lost. There's no backup, no recovery. The data simply vanishes along with the container. The key takeaway is that storing session data locally in Cloud Run containers is fundamentally unreliable. It creates a poor user experience where people lose their progress, shopping carts, login status, and other important session information whenever containers restart. This is why we need external session storage solutions. HTTP sessions store user-specific data that needs to persist across multiple requests. Think of it as the application's memory about each individual user. Let's explore the most common types of session data with practical examples. First, authentication status. This tells the application who the user is and whether they're logged in. It includes their user ID, role permissions, and login information. Shopping cart data is crucial for e-commerce sites. It remembers what items users have selected, quantities, pricing, and any discount codes they've applied. User preferences customize the experience. This includes language settings, display themes, time zone preferences, and notification configurations. Multi-step forms need to remember data between pages. This prevents users from losing their progress when navigating through complex registration or checkout processes. The key point is persistence. Session data remains available across multiple requests from the same user, creating a seamless and personalized experience throughout their interaction with the application. All of this session data works together to provide users with a personalized and consistent experience, remembering their choices and state as they navigate through the application. Cloud Run containers are ephemeral, meaning they're temporary and short-lived. They can start up, handle requests, and then shut down or be recycled at any time. When we store session data locally inside these containers, we run into a serious problem. Each container might have different user sessions stored in its memory, but here's the problem. When containers are recycled or shut down, all that session data disappears with them. Users lose their login status, shopping carts, and preferences. Think of it like this analogy. Imagine you're working at a temporary desk that could be taken away at any moment. You wouldn't keep your important documents there, would you? Instead, you'd move those important documents to a secure filing cabinet that stays put, even when your temporary desk is removed. This is exactly why we need external session stores for Cloud Run. We move session data outside the ephemeral containers to a persistent storage system. Redis, available through Google Cloud's Memory Store service, is an excellent choice for this external session storage. It's fast, reliable, and designed specifically for this type of data. With external session storage, when containers are recycled, the session data remains safe and accessible. Users maintain their sessions seamlessly, regardless of what happens to individual containers. This external session storage approach ensures data persistence, improves user experience, and allows Cloud Run to scale efficiently without losing important session information. Redis is an in-memory data structure store that has become incredibly popular for session storage. Google Cloud offers Memory Store, which is their fully managed Redis service that handles all the infrastructure complexity for you. Redis excels at session storage because of two critical characteristics: low latency and high concurrency. Let me show you what these mean and why they matter so much for your applications. First, low latency. When a user makes a request, your application needs to quickly retrieve their session data. Redis stores everything in memory, not on disk, which means access times are incredibly fast, typically under 1 millisecond. Second, high concurrency. This means Redis can handle thousands of users accessing their session data simultaneously without slowing down. Traditional databases might struggle with this load, but Redis is specifically designed for high-performance concurrent access. These characteristics directly impact user experience. Imagine a user logging into your application. With Redis session storage, their login state is retrieved in under a millisecond, and this works smoothly even when thousands of other users are doing the same thing simultaneously. This is why Redis and Memory Store are the go-to choices for session storage in modern web applications. The combination of speed and scalability ensures your users have a smooth, responsive experience, even as your application grows to serve more and more users. Understanding HTTP sessions requires following the complete data flow from user to server and back. Let's walk through this step by step, starting when a user first visits your website. When the user visits your site, their browser sends an HTTP request to your Cloud Run service. This is the first interaction in what will become a session. Since this is the user's first visit, your Cloud Run service generates a unique session ID. Think of this as a special ticket number that will identify this user's session. The service then creates a cookie containing this session ID and sends it back to the user's browser. The browser automatically stores this cookie for future requests. Meanwhile, your Cloud Run service stores the actual session data in Memory Store, a Redis database. This data is linked to the session ID we just created. Now let's see what happens when the same user makes a subsequent request to your website. On the user's next request, their browser automatically includes the cookie with the session ID. This happens transparently. The user doesn't need to do anything special. Your Cloud Run service extracts the session ID from the cookie and uses it to retrieve the corresponding session data from Memory Store. This gives your application access to the user's previous state and preferences. This creates a seamless user experience. The session persists across multiple requests, allowing features like shopping carts, user preferences, and authentication to work properly in a stateless Cloud Run environment. Cookie security is critical for protecting user sessions. Without proper security measures, session cookies become vulnerable to various attacks that can compromise user accounts and sensitive data. There are 4 essential security attributes that must be implemented to protect session cookies. Each one addresses a specific type of attack vector. First, cryptographic signing prevents cookie tampering. When a cookie is signed with a secret key, any modification to the cookie data will be detected, making it impossible for attackers to forge valid session cookies. The secure attribute ensures cookies are only transmitted over encrypted HTTPS connections. This prevents network eavesdropping attacks, where malicious actors intercept unencrypted HTTP traffic to steal session cookies. The HT-only attribute prevents client-side JavaScript from accessing session cookies. This protects against cross-site scripting attacks, where malicious scripts try to steal cookies and hijack user sessions. Finally, the same site equals strict attribute protects against cross-site request forgery attacks. It ensures cookies are only sent with requests originating from the same site, preventing malicious websites from making authenticated requests on behalf of users. By implementing all 4 security attributes together, you create a robust defense system for session cookies. Cryptographic signing prevents tampering, secure ensures encrypted transmission, HT only blocks script access, and same site prevents cross-site attacks. These measures work together to protect user sessions from malicious actors. Now we need to address a critical challenge. How does Cloud Run connect to private network resources? This is where the VPC connector becomes essential. On the other side, we have our memory store instance sitting inside a virtual private cloud, protected by a private IP address that Cloud Run cannot directly access. The problem is clear. There's a gap between Cloud Run and the private network. Cloud Run cannot directly reach resources with private IP addresses. This is where the VPC connector comes to the rescue. Think of it as a secure bridge or tunnel that connects your Cloud Run service to your virtual private cloud. Let me show you how this works. On the left, we have our Cloud Run service running in Google's managed environment. On the right, we have our memory store instance safely tucked away in a virtual private cloud with its private IP address. Now, here's the magic. The VPC connector acts as a secure tunnel, creating a bridge between these 2 environments. With the VPC connector in place, data can now flow securely from Cloud Run through the connector and into the private network to reach memory store. Let me highlight the key benefits of using a VPC connector for this connection. First, it provides secure connectivity. The VPC connector creates an encrypted tunnel, ensuring that data traveling between Cloud Run and your private resources remains protected. Second, it enables private IP access. Without the VPC connector, Cloud Run cannot reach resources with private IP addresses. The connector makes this possible. Finally, it's seamless integration. Once configured, your Cloud Run service can connect to VPC resources as if they were on the same network, making development and deployment much simpler. The VPC connector is the essential bridge that makes private network connectivity possible for Cloud Run services. In the next sections, we'll dive deeper into the specifics of setting up and configuring these components. When working with memory store for Redis, understanding the different instance characteristics is crucial for making the right choices for your application. Let's explore the key features that define memory store instances. Memory store offers 2 main tiers. The basic tier provides a single-zone Redis instance with no automatic failover, making it cost-effective for development and testing. The standard tier offers multi-zone deployment with automatic failover for production workloads requiring high availability. Memory store instances can be configured with memory sizes ranging from 1 GB up to 300 GB. Choose your memory size based on your application's data requirements and expected cache hit ratios. Each memory store instance receives a private IP address within your VPC network. This ensures secure communication between your Cloud Run services and the Redis instance, with no traffic going over the public internet. Unlike serverless services that scale to 0 and charge only for usage, memory store instances are billed based on uptime. This means you pay a fixed hourly rate for as long as the instance exists, regardless of whether it's actively being used. When choosing your memory store instance size, consider your expected concurrent sessions, average session data size, desired cache performance, and future growth. Start with a smaller instance and monitor usage patterns, then scale up as needed to optimize both performance and cost. Remember, memory store instances provide reliable, high-performance Redis caching with private network access, but require careful planning due to their uptime-based billing model. A virtual private cloud, or VPC network, is one of the fundamental building blocks of Google Cloud infrastructure. Think of it as your own private section of the internet within Google's massive cloud platform. Imagine Google Cloud as a vast digital landscape. Without proper organization, all your resources would be mixed together with everyone else's, creating security and management challenges. A VPC network creates logically isolated private networks within Google Cloud. Each VPC acts like a separate, secure environment where you have complete control over your network configuration. Within each VPC network, you can deploy various Google Cloud services. In our case, we're particularly interested in how Cloud Run and Memory Store work together within the same VPC for secure communication. Now let's focus on the key benefits that VPC networks provide for your cloud infrastructure. The first major benefit is security and isolation. Your VPC network acts like a protective barrier, ensuring that your resources are completely separated from other users' resources in Google Cloud. The second benefit is complete network configuration control. You can define IP address ranges, create subnets, set up firewall rules, and control how your services communicate with each other. Here's where it gets interesting for our session storage setup. When both Cloud Run and Memory Store reside in the same VPC network, they can communicate securely and efficiently using private IP addresses. Let's summarize the key takeaways about VPC networks and why they matter for your session storage architecture. First, VPC networks provide logical isolation within Google Cloud, creating your own private network space. Second, you get complete control over network configuration, including IP ranges and firewall rules. Third, this enhances security through private networking that keeps your traffic internal. Fourth, memory store instances reside within your VPC for maximum security. And finally, this setup enables secure communication between Cloud Run and Memory Store without exposing traffic to the public internet. Understanding VPC networks is crucial because they form the foundation for secure, scalable cloud architectures. In our next section, we'll explore how VPC connectors enable Cloud Run services to access resources within your VPC network. Understanding how VPC connectors scale and how you're billed for them is crucial for managing costs effectively in your Google Cloud infrastructure. VPC connectors automatically scale to handle your application's traffic demands. This means they can dynamically adjust their capacity based on the volume of requests flowing through them. When traffic increases, the connector automatically scales up to handle more connections. When traffic decreases, it scales back down. This happens seamlessly without any manual intervention. However, here's the important part about billing. VPC connectors are not pay-per-use. Instead, you're billed for the connector's uptime, meaning you pay for how long the connector exists, regardless of how much traffic flows through it. This means that even if your connector is idle with no traffic, you're still being charged for its existence. The billing clock keeps ticking as long as the connector is provisioned in your project. Because of this billing model, it's crucial to manage your VPC connectors efficiently. You should monitor their usage and ensure they're appropriately sized for your application's actual needs. Here are the key takeaways. First, VPC connectors scale automatically, but you pay for uptime, not usage. Second, monitor your connectors regularly to avoid unnecessary costs. And third, delete unused connectors promptly to stop billing. When building Cloud Run applications that need session storage, you have three main options to choose from. Each has different strengths and trade-offs that make them suitable for different scenarios. Here are your three main options: Memory Store for ultra-fast in-memory caching, Cloud SQL for traditional relational database storage, and Firestore for flexible document-based storage. Let's compare these options across four key decision factors that will help you choose the right session store for your application. For latency, Memory Store is the clear winner with sub-millisecond response times since data is stored in memory. Cloud SQL typically responds in 5 to 10 milliseconds, while Firestore can take 10 to 50 milliseconds depending on your location and query complexity. For reliability, Cloud SQL and Firestore offer higher SLA guarantees. Cloud SQL provides 99.95% uptime, Firestore offers 99.99%, while Memory Store provides 99.9% uptime. Operational overhead varies significantly. Firestore is fully managed with minimal maintenance required. Memory Store needs some configuration and monitoring. Cloud SQL requires the most operational work, including backups, updates, and capacity planning. Pricing models differ too. Firestore uses pay-per-use pricing, making it cost-effective for low-traffic applications. Memory Store charges per hour for reserved capacity. Cloud SQL is typically the most expensive with hourly charges plus storage costs. Here's when to choose each option. Pick Memory Store for high-performance applications where every millisecond counts. Choose Cloud SQL when you need complex queries and ACID transactions. Select Firestore for applications with unpredictable traffic that need minimal operational overhead. Remember these key points when making your decision. Memory Store excels at speed, but requires more operational investment. Cloud SQL provides powerful querying capabilities, but needs the most maintenance. Firestore offers simplicity and cost-effectiveness for variable workloads. Always consider your specific traffic patterns and latency requirements when choosing your session store. A service level agreement, or SLA, is essentially a promise from your cloud provider. It's their guarantee about how reliable and available their service will be. SLAs are typically expressed as uptime percentages. Let's look at what different SLA levels actually mean in practice. Here we see 3 common SLA levels. Basic services might offer 99.9% uptime, standard services 99.95%, and premium services 99.99%. But what do these percentages actually mean? Let's translate these percentages into actual downtime. This will help you understand what each SLA level really means for your application. Here's what these SLA percentages mean in real downtime. A 99.9% SLA allows for almost 9 hours of downtime per year, while a 99.99% SLA only allows for about 53 minutes annually. Now here's the important part. Higher SLAs typically come with higher costs. You're paying for better infrastructure, redundancy, and guaranteed performance. This chart shows the typical cost relationship. Premium SLAs can cost several times more than basic ones. You need to balance your reliability requirements with your budget. Let's look at some real Google Cloud examples. Different services offer different SLA levels, and this affects both cost and reliability. For session storage, Memory Store offers a 99.9% SLA for basic Redis instances. Cloud SQL provides 99.95% for regional instances, while Firestore can offer 99.99% with multi-region deployment. The key takeaway is to choose an SLA that matches your application's requirements. Don't overpay for reliability you don't need, but ensure you have enough uptime for your users' expectations. Session Affinity might sound like the perfect solution for managing user sessions in Cloudrun, but it's actually a common misconception that can lead to serious problems. Session Affinity means that all requests from the same user are always routed to the same container instance. This seems logical. If the user's session data is stored locally in that container, they'll always find their data there. Here's the critical flaw. Cloudrun containers are completely disposable. They can be shut down at any time due to scaling, updates, or resource management. When this happens, all local session data is permanently lost. The key misconception is thinking that Session Affinity provides reliable session storage. In reality, Affinity is only a performance optimization that can reduce latency, but it cannot guarantee data persistence. Remember, Session Affinity is not the same as session persistence. While Affinity can improve performance by reducing latency, containers in Cloudrun remain disposable. You must always use external storage like Redis or Memory Store for reliable session management. When working with Google Cloud resources like Memory Store and VPC connectors, one critical aspect that developers often overlook is proper resource management. Let's see what happens when resources are left running unnecessarily. As these resources run continuously, they accumulate charges. Memory store instances can cost over $100 per month, and VPC connectors add additional fees. This is especially problematic in development and testing environments where resources may not be needed 24/7. The solution is to shut down these resources when they're not in use. Let's look at the specific gcloud commands you'll need to manage these resources effectively. Here are the essential gcloud commands for resource cleanup. First, to delete a memory store instance, use the Redis instances delete command with your instance name and region. For VPC connectors, use the Compute Network's VPC Access Connectors delete command. Now let's look at some best practices for resource management that can save you significant money and prevent billing surprises. First, set up automated shutdown scripts that can turn off development resources outside business hours. Use development schedules that match your team's working hours. Set up billing alerts to catch unexpected charges early. Tag your resources by environment so you can easily identify what can be safely shut down. And always document your cleanup procedures for your team. By following these practices, you can reduce your cloud costs by 60 to 80% in development environments. Remember, every hour these resources run unnecessarily is money that could be better spent on actual development and innovation. Before we can create our memory store instance and VPC connector, there's an important prerequisite step we need to complete first. We must enable the necessary Google Cloud APIs that power these services. We need to enable two specific APIs. First, the Redis API, which allows us to create and manage memory store instances. Second, the VPC Access API, which enables us to create VPC connectors for secure communication between Cloud Run and memory store. There are two convenient ways to enable these APIs. You can use the Google Cloud Console through your web browser, or you can use the gcloud command line tool. Let me show you both approaches. The first method uses the Google Cloud Console web interface. You'll open the console in your browser, navigate to the APIs and Services section, then search for and enable each API individually. This method is great if you prefer a graphical interface. The second method uses the gcloud command line tool, which is faster and perfect for automation or if you prefer working in the terminal. With the gcloud command line tool, you can enable both APIs with just two simple commands. First, run gcloud services enable redis.googleapis.com to enable the Redis API. Then run gcloud services enable vpcaccess.googleapis.com to enable the VPC Access API. Here's the key takeaway. Enabling these APIs is a prerequisite step that must be completed before you can create any memory store instances or VPC connectors. Without these APIs enabled, your subsequent commands will fail. Remember, this is a one-time setup per Google Cloud project. Once you've enabled these APIs, you can create multiple memory store instances and VPC connectors without needing to enable them again. Choose the method that works best for your workflow. Now we'll create a memory store Redis instance using the gcloud command line tool. This is where we'll store our HTTP session data for Cloud Run applications. The basic command structure starts with gcloud Redis instances create, followed by several important parameters that define our instance configuration. Let's break down the essential parameters you need to specify when creating your memory store instance. Here's a complete example command that creates a Redis instance named MySessionStore in the US Central 1 region with 1 GB of memory connected to the default VPC network. The creation process typically takes 2 to 5 minutes. During this time, Google Cloud provisions the Redis instance, configures networking, and sets up monitoring. Here are the key takeaways for creating your memory store instance. Choose a descriptive instance ID. Select a region close to your Cloud Run services. Start with 1 GB for testing, and ensure your VPC network is properly configured. Now that we have our memory store instance created, we need a way to view and monitor our existing instances. The gcloud Redis instances list command is our go-to tool for this task. The command syntax is straightforward. We simply type gcloud Redis instances list to get a comprehensive view of all our memory store instances. When we run this command, it returns a table with detailed information about each instance. Let me show you what a typical output looks like. Each column provides crucial information. The name column shows your instance identifier, which you use in other gcloud commands. The region tells you where your instance is deployed, which affects latency and compliance requirements. The tier column shows whether you're using basic for development or standard for production with high availability. The host column displays the internal IP address that your Cloud Run services will use to connect to Redis. Finally, the status column is critical for monitoring. Ready means your instance is operational, while creating indicates it's still being provisioned. This command is invaluable for several monitoring and management tasks. Let me show you some practical scenarios. First, health monitoring. You can quickly check if all your instances are ready before deploying applications, monitor for any failed states, and verify everything is working after maintenance. Second, resource inventory management. You can track memory usage patterns, identify underutilized instances for cost savings, and plan capacity for future scaling needs. Third, connection configuration. The list command provides the exact IP addresses and ports your applications need, helping you configure environment variables and verify regional placement for optimal latency. Remember, this command is your window into the health and status of your Redis infrastructure. Regular monitoring helps prevent issues and ensures your session storage is always available for your Cloud Run applications. Now that we have our memory store instance ready, we need to create a VPC connector. This connector acts as a bridge that allows our Cloud Run services to securely communicate with resources inside our VPC network. The VPC connector is created using the gcloud command line tool. Let me show you the complete command structure and break down each component. Let's break down each parameter. First, we specify the connector name, in this example, my-VPC connector. Choose a descriptive name that identifies the purpose of this connector. The region parameter specifies where the VPC connector will be created. This should match the region where your Cloud Run service and memory store instance are deployed for optimal performance. The subnet parameter specifies which subnet in your VPC network the connector should use. The default subnet is commonly used, but you can specify a custom subnet if needed. The most critical parameter is the IP address range. This defines the pool of IP addresses that the VPC connector can use. The range must be large enough to handle your expected traffic load. For most applications, a 28 range providing 16 IP addresses is sufficient. However, if you expect high traffic or multiple services, consider using a 27 or 26 range for more capacity. Here's a complete example command that creates a VPC connector named Session Connector in the US-Central 1 region with a 28 IP range. This connector will enable your Cloud Run services to access memory store securely. Now we're ready to deploy our Cloud Run service with the VPC connector and environment variables. This is where everything comes together to enable secure communication with memory store. The deployment command has several key components. We start with the basic gcloud run deploy command, specifying our service name. The VPC connector flag is crucial. It links our Cloud Run service to the VPC connector we created earlier. This enables private network access. The set-envars flag configures the Redis IP environment variable with the private IP address of our memory store instance. We also specify the region to ensure our service deploys in the same region as our VPC connector and memory store instance. Let's visualize how these components work together during deployment. Here's the deployment architecture. Our Cloud Run service connects through the VPC connector to reach memory store securely. The Redis IP environment variable contains the private IP address of our memory store instance, allowing our application code to connect directly. Now let's walk through the actual deployment steps. First, ensure your application code is ready and can use the Redis IP environment variable to connect to Redis. Next, build your container image and push it to Google Container Registry or Artifact Registry. Then deploy your service using the VPC connector flag to enable private network access. Finally, set the Redis IP environment variable to your memory store instance's private IP address. Let's review the key points about deploying with VPC connector and environment variables. The VPC connector is essential for secure private network access between Cloud Run and memory store. Environment variables provide a clean way to pass configuration, like the Redis IP address, to your application. Using the private IP address ensures your Redis communication stays within Google's secure network. Remember that all components, Cloud Run service, VPC connector, and memory store must be deployed in the same region for proper connectivity. When you no longer need your memory store instance, you can delete it using a simple gcloud command. However, this is a critical operation that requires careful consideration. The command to delete a memory store instance is gcloud redis instances delete, followed by your instance name. This command will permanently remove the instance and all its data. It's crucial to understand that deleting a memory store instance will permanently destroy all session data stored within it. This includes all user sessions, cache data, and any other information stored in Redis. Before deleting your memory store instance, consider whether you need to back up any data. While session data is typically temporary, you might want to export configuration settings or ensure no critical user sessions are active. Here's the recommended process for safely deleting a memory store instance. First, verify your instance name and region. Optionally, stop your Cloud Run services to prevent connection errors. Then, run the delete command and confirm when prompted. Remember, deleting a memory store instance is permanent and irreversible. Always double-check the instance name and consider whether you need any backups before proceeding with the deletion. Now that we've learned how to create and use VPC connectors, it's equally important to understand how to properly delete them when they're no longer needed. This helps avoid unnecessary costs and keeps your Google Cloud environment clean. Before deleting a VPC connector, there's a crucial first step. You must ensure that no Cloud Run services are actively using the connector. Attempting to delete a connector that's still in use will result in an error. Step 1 is to verify that no Cloud Run services are currently using your VPC connector. You can list all your Cloud Run services and check their configurations to ensure none are referencing the connector you want to delete. Step 2 is executing the deletion command. The gcloud command follows a specific pattern. Gcloud compute networks VPC access connectors delete, followed by the connector name and the region where it was created. Let me show you what happens during the deletion process. Initially, if a Cloud Run service is still connected to the VPC connector, the deletion will fail to protect your running services. Once you've confirmed no services are using the connector, the deletion command will safely remove the VPC connector from your Google Cloud project. Here are some key considerations to keep in mind when deleting VPC connectors. The deletion is permanent and cannot be undone. However, billing stops immediately, which helps control costs. Make sure to update any service configurations that might reference the deleted connector. To summarize, deleting a VPC connector is straightforward once you've verified that no Cloud Run services are actively using it. Use the gcloud compute networks VPC-access connectors delete command with the connector name and region. This cleanup step is important for maintaining an organized and cost-effective Google Cloud environment. We've covered a lot of ground in this comprehensive guide to Cloud Run HTTP sessions. Let's recap the 3 most important takeaways that will help you build robust, scalable applications. First, external session storage is absolutely crucial for Cloud Run applications. Since Cloud Run is stateless and instances can scale up and down automatically, storing session data locally simply won't work reliably. Second, Memory Store with Redis provides an excellent solution for session storage. It's fast, reliable, and integrates seamlessly with Google Cloud services. The in-memory nature of Redis makes it perfect for the quick read and write operations that sessions require. Third, VPC connectors are the bridge that enables secure, private network connectivity between your Cloud Run services and memory store instances. They handle the networking complexity so you can focus on your application logic. Here's how these components work together in your architecture. Cloud Run connects through the VPC connector to reach your memory store instance, creating a secure and efficient session storage solution. Now it's time to put this knowledge into practice. Here are some concrete next steps you can take to deepen your understanding and build real-world experience with these technologies. Start by experimenting with these concepts in your own projects. Try different session storage configurations to see how they perform. Explore advanced VPC networking features to understand the full capabilities available to you. And don't forget to monitor and optimize your session performance as your application grows. Remember, the best way to truly understand these concepts is through hands-on experience. Build something, break it, fix it, and learn from the process. The Google Cloud documentation and community are excellent resources as you continue your journey.